Let's consider the following concrete example. We have a copper rod with the length 80, in fact centimeters. It's insulated and it's kept at a constant temperature equal to 0 Celsius at the boundary on this rod. The copper has a density 8.92, the conductivity is 0.92, and the specific heat is 0.95. We also have in this example given the initial temperature, which is given by this function. So it starts at 0, grows in the middle of the rod, it reaches its maximum, and then it decreases to 0 again. So the initial temperature is given by 100 sine pi x over 80. We are going to find how long time it's going to take until the maximum temperature at this point is equal to 50 degrees. You see that the temperature starts at 100 degrees, the maximum temperature, and it decreases to 50 degrees after some time, and we are going to find this time. So how are we going to proceed? We know that the general solution of the one-dimensional heat conduction problem is given by this infinite series, and this lambda n is, as we know, given by Cn pi over L. So in our case, C is this expression K over sigma rho. And we know all these constants, so it's possible to find this number. We know that the initial temperature Ux of 0 is given by 100 sine px over 80. And let's just write out some additional terms. We know that this is the only function, but in this special case we can do some small trick in order to find all these coefficients. We know that when t is equal to 0 from this general expression, then this term is always equal to 1. So it's rather easy to write out some finite number of terms. We start with b with n equal to 1 here, and we have sine px over 80. Multiply this with 1 in each case, plus b2 sine 2, and in this case n is equal to 2, so therefore we replace n by 2. And in the third term we replace n with 3, and so on. And to compare, this term is very similar to this term, and in these cases, when there are such a similarity, then it's rather easy to find the coefficients b1, b2, b3, and so on, because we know that this is the only expression for the initial temperature. So if we just add some 0 terms here, we see that as 0 terms we make them similar to the terms of the Fourier series. Then we see that the first term b1 must be equal to 100, the second term b2 must be equal to 0, the third term must be equal to 0, and so on. All terms except the first one must be equal to 0. This is what we have written here. B1 is equal to 0, to 100, B2 is equal to 0, and so on. Therefore, this infinite series consists only of one term, namely the first term. So it's very easy to write the solution in this case. U of xt is equal to 100 times sine px over 80 multiplied with the exponential function in the of this guy when n is equal to 1. So in this case we only have minus 0.001785 t, and we have no other terms. So in this case it's rather simple to find the maximum temperature. The maximum temperature is given when this guy is equal to 1 in the middle of the rod. So we know that the temperature here is 100 times the exponential function of this guy, and it should be equal to 50 because that was our question. What is T then? And in order to find this T, it's rather trivial. We just divide both sides of this equation with 100, get this equation, taking the logarithm on both sides, and then we obtain this equation, and immediately we can divide with this constant and we get the time t. And computing this numerical value, we find that it takes 388 seconds until this maximum temperature is 50 Celsius.